Department of Physics, Manipur University. Previously, she was serving at NERIS as an associate professor and as assistant professor also there. She did PhD, MSc from NEHU, experimental physics, spectroscopy.
Yes.
Is it?
Yes.
Okay. She's an expert of spectroscopy. Finally, spectroscopy is nothing but spin and all these transition. I invite Professor Dr. T.S. Gomti Devi to deliver her talk. Thank you. So they give you 45 minutes, but no problem, plus minus you take.
Oh, yes. Oh, thank you, sir. She come.
She's now my lizard. Next up.
Thank you, Professor N.G. Nimai Singh, for a nice introduction. Thank you so much. Then, good afternoon, ladies and gentlemen, and participants. The title of my talk is Spin in Quantum Mechanics and its Applications. So, before starting my talk, let me just explain what is the quantum mechanics all about. As you have already known that quantum mechanics is the branch of science which deals with the microparticles like atomic and subatomic particles. So, by studying these subatomic or atomic particles, you can provide the physicochemical properties of the atomic and the subatomic particles, then their structures, then spectral behavior and the reactions that is taking place between atoms and molecules like that. So, that is why today's actually we will be talking about from the subatomic particles from the atoms, like when the electrons here I am just showing here also. This is the structure of the atoms where the electrons are revolving around their nucleus in their respective orbits. So, here when the electron is revolving around their nucleus in their respective orbits, they have their orbital angular momentum. So, that is why let us come to the spin. Spin also has intrinsic angular momentum. So, what is spin? What is the history of the spins? How the spin is coming up? Then what is the applications of the spin in the characterization of the compound that we will be discussing. So, the contents of my talk is what is spin, the history of the spins, importance of Dirac equation, O. Stern and W. Gerlach experiment, spin-orbit interactions, difference between the Sommerfeld level and the Dirac levels, then electron spin resonance. So, what is spin? When we talk about the spin, then it is the fundamental property of the particles which describe the which describe the angular and the magnetic properties of the particles. So, it also referred to as an intrinsic angular momentum of an object in the frame in which the center of mass is at rest. So, classically if we considered, we can consider a macroscopic object which has been rotating through an axis through their center of mass. So, like this. So, the macroscopic body which is rotating through their axis of rotation. But when we talk about the elementary particles, it is difficult to set in this way that it is rotating in its own axis because of its tiny size and also due to the this nature of the quantum mechanics. So, this interaction, when we talk about these atomic particles, they are having spin in two directions. One is the spin up and other is the spin down. And it is also associated with the magnetic moment. And this magnetic moment, it has been given by this formula nu equal to G Q by twice mc into S, where G is the G factor and its value is found to be 2.003 something like that, and Q is the charge of the particles, and m is the mass, C is the velocity of light, and S is the spin. And this is for the spin up and this is for the spin down. And in the physical manifestation of the skin is about its magnetism only. So, that is why it is predicting the magnetic properties of the quantum particles. So, here what are the electron spins? Here we can consider here that this is the spin which is also spinning around their axis. Here the North Pole and South Pole. Here it is starting from the magnetic field starting from the North Pole to the South Pole. Even here also the same thing. So it shows the spin which is in the upward direction. And when it is upside down, you see the North Pole is in this direction. The magnetic field is starting from the north to the south. So this is the spin which is flipped down. So and because of the Pauli exclusion principle, the two electrons cannot have in the same quantum state that you know already. So that is why this is not possible and this is possible, spin up and spin down. So let's come to the history of the spin. So H. Compton in 1921, he postulated the phenomenon of the ferromagnetism. Here he said that it is associated with the intrinsic magnetic moment of the electrons rather than the orbital magnetic moment. Orbital magnetic moment means when the electron is revolving around the nucleus, it possesses the orbital magnetic moment. In addition to this, the intrinsic magnetic moment is also associated. So this is the picture for the H. Compton, and he also mentioned that the G factor must be greater than unity. So although whatever he is saying is reasoning classically, but the electron spin is proportional to H cross. H cross, you know already, is H by twice pi. H is the Planck's constant. So that is why it also accounts for the magnetic moment. However, the concept of spin was attracted widely in 1925 by G. Uhlenbeck and S. Goudsmit, who postulated that the electron has the intrinsic spin of S equal to H cross by 2 and G equal to 2. So in order to derive this, he used, this is the picture for the Uhlenbeck and Goudsmit, he used the Bohr-Sommerfeld quantum theory. Quantum theory is based to explain the fine structure of the atomic spectral lines in the present and their behavior in the applied magnetic field. So here I would like to mention that the simplest elements, for this in other elements is the hydrogen atom that you know already. So this hydrogen atom is the one where it has only one electron which is revolving around the nucleus. But when you have excited this atom, then what happens is electrons will be excited to the higher excited state. Then after coming down, there is emission of radiation. So in this hydrogen spectrum, there are already 5 series of lines, isn't it? This is the Lyman, Balmer, Pascal, Brackett and Fun series. So of this 5 series, Balmer lies in the visible region, and the most prominent lines are this violet, then blue, green, and this red. Red is the most distinct one. So this red color, when it has been observed with a high sophisticated this spectrometer, then it has been observed that this line is again split into 2. That we used to call as the doublet. So this doublet is also known as the fine structure of the atomic spectral lines. So this fine structure, why it is so, it has been studied by Bohr and Sommerfeld, and that relation has been used by Uhlenbeck and this Goudsmit in order to explain the existence of the spin. And let us come to in 1913, let us just go back. Here Bohr also discovered about the orbital angular momentum. So in that they mentioned that any change in the component of the angular momentum in one axis can occur as an integer of H cross. So that is why, somehow one author has mentioned that this can also be applied to the spin because it is approximately proportional to the H cross. Okay, so that is why when it is spin up, the z direction, it is the plus half, and when it is in the minus z, then it will be minus half. And let's come to the Schrödinger equation for the non-relativistic quantum mechanical system. So Schrödinger equation that you know already is a partial differential equation that governs the wave function of a non-relativistic quantum mechanical system. So this is the time-dependent Schrödinger equation. And then not only this non-relativistic quantum mechanical system, Schrödinger equation also he derived in the relativistic wave equations. So this is the equations. And this del square minus 1 by c square del square by del t square is called the D'Alembert operator. So this operator, when you substituted, this equation is also known as the Klein-Gordon equation for free particles. So the not only for the non-relativistic means when the particle is moving less than the velocity of light. So if the particle is moving very fast, then it is become the relativistic wave equation. So when this relativistic wave equation, one for the Schrödinger equation for the relativity wave equation, and one is the Klein-Gordon equation, for the free particles, when it has been observed to study for the atomic physics, there is some mismatch or discrepancy is coming up, because there are some stationary values are there, whose value is found to be only half as compared to this experimental value. So this is the one. So this Pauli pointed out that this discrepancy is due to is removed by the introduction of the spinning of the electrons. So that is why, according to Pauli hypothesis, the electrons possess a spin of angular momentum h cross by 2 and the magnetic moment of this E h cross by 2 pi MEC. So Pauli and Darwin fitted the hypothesis and found that this problem of the stationary states has been solved. However, this in 1928, Paul Dirac, he pointed out that this spin theory has certain objections. So the first objection he mentioned is that if this electron is moving in a central force field, then this their resultant atomic the orbital angular momentum should be its magnitude should be constant. Let me repeat, if the electron is moving in a central force field, then the magnitude of the resultant orbital angular momentum should be constant. But actually it is not so. Then one more thing is, in the case of this non-relativistic Schrodinger equation, we observe that I s cross del by del t psi equal to E psi. So del by del t and E, they are in linear functions. So that is why if you want to find it out psi naught at time t0, then it is easy to find it out psi naught at any time t. But in the case of relativistic equation, del by del t or E functions, they are non-linear. So that is why Dirac said that there is some discrepancy there, and Schrodinger equations works well for the non-relativistic but fail in the high speed. So that is why he fixed this by combining the quantum mechanics and relativity. And this is the Hamiltonian that he mentioned, Hamiltonian equal to C alpha dot P plus beta m0 C square. Here alpha and beta need not be number, and they are independent of position, time, then this momentum and energy. And P denote the three-dimensional momentum vector. And this eigenvalue equations for the Schrodinger equation is h psi equal to E pi. This is written as, after substituting the value of h, we are getting this value. And there is also one condition that he has mentioned, that any solution of the above equation must be the solution of the Schrodinger relativistic equation for this equation. So that is why from this equation number 1, he multiplied by this factor, and this equation is agree well with equation number 2 if the following conditions are satisfied. So there is alpha square and beta square, those parameters, the square should be equal to 1, and those other pairs, they are anti-commute to each other. It means their product should be equal to 0. And these quantities of this type is represented by the following matrices. This is the beta value, this is a 4x4 matrix. This is alpha x, beta, alpha y, and alpha z, because it is the vector component, so it has 3 components. And he also derived, actually derivation and all I haven't shown here. So here for the free particles, he observed 4 spinors. One is the positive energy spinner and the other is the negative energy spinners. So the positive one, this one U plus is the electron which is, the free particle which is in the upward direction, spin flip up, and this is flip down. And for the negative energy spinners also, they are getting spin flip up and flip down. And these terms, you know already, they are the components of the this momentum, energy, mass, and then velocity of light, etc. So they describe the particles with the spin up and spin down. And Dirac also, equation there is in central field proved the presence of the spin angular momentum S equal to I cross by 2. So this one I haven't shown here. This is only the free particles. And this Dirac equation also used in the quantum chemistry in ab initio calculations. So in the Dirac theory, as I already mentioned, that there are positive energy spinners, positive and negative energy. So this has been, I have been shown here. This is the positive energy and this is the negative energy. Positive energy can be extended up to infinity. Negative energy also can be extended up to infinity. So this eigenvalue energy for the free energy is given by this formula. So for the minimum energy, this momentum is 0, so E become plus minus m0 c square. So this is the positive part and this is the negative part. So the energy difference between these two, or you can say energy gap, is 2m0 c square, isn't it? So that is why when a photon of energy which is greater than 2m0 c square has been applied, then the electrons which are there in the negative energy move to the positive energy and they making a hole in the negative energy. So this negative energy is known as the hole is known as the Dirac hole. So this Dirac hole, when another electron jump and fill it up, then this one with again another vacant seat will be there. Then another electron will jump and then the Dirac hole will keeps on moving like this. So in the semiconductor physics, these holes act as the positive charge and is called the positron. So in the Dirac theory, the positron is considered as an unoccupied state of the energy state in the Dirac theory. So this Dirac was awarded Nobel Prize in 1933 for his work in the development of the Dirac equation, which mathematically explain the concept of the electron spin. And this presence of the spin has been shown experimentally by O. Stern and G. Gerlach experiment. Here, they have in the oven this silver atom has been coming out, stream of the silver atom light is allowed to pass through it, and in between this is the inhomogeneous this one magnetic field. So electron is allowed to pass through this field, and when it is has been collected in the photographic plate, then you have observed two distinct parts. One is the up and the other is down. So this shows the presence of the spin. One is spin up and spin down. And for this experiment, they haven't got the Nobel Prize. But O. Stern, he has observed. He was awarded Nobel Prize for his development of molecular ray method. And for the discovery of magnetic moment of the protons. Okay, but whatever his work is based concept is taken from the O. Stern and Gerlach experiment only. Okay. Now let's come to the spin orbit interaction. So here, as I already mentioned, when the electron is revolving around the nucleus, it has this orbital magnetic moment, isn't it? So while rotating around this one magnetic, along the orbit, it also rotating, spinning around its axis. So that is why while rotating, it produces its internal magnetic field. It produces, isn't it? When the electron is revolving around a nucleus along its own orbit, it produces its internal field. But while spinning in its own axis, also it produces the magnetic moment. So the interaction between the magnetic moment and this internal magnetic field is leading to the splitting of this spectral line. Okay, so that is why whatever the splitting of the spectral line that we have already mentioned in the previous also, that fine structural lines. Why this fine structural line has been taking place? So there are two factors. One is due to the spin orbit interaction and the other is the relativistic interaction. So in this spin orbit interaction between the magnetic field which is produced by the rotation of the electron around its orbit and the magnetic moment due to the spinning of the electrons. And this spin orbit interaction is very much important in one electron atom and heavy atoms also. And when the observer is moving with a velocity v in an external magnetic field, then magnetic field is given by this formula. So this magnetic field acts on the electron magnetic moment. So the electron and the spin magnetic moment can assume different orientations in the internal magnetic field B. So these orientations or interaction of this magnetic moment and the magnetic fields is represented by the this magnetic potential energy of the orientation given by this. And by substituting the value of mu s and the b, you are obtaining this formula. And SL formula, to you know, J is the these are the quantum numbers only. Total this one quantum number, this is orbital quantum number, and this is the spin quantum number. And for the hydrogen-like atoms, when the electron move in a Colombian field, the the potential Br is given by minus ZE by R, and then dB by dr also you can easily find it out. So after substituting all the values, you are finding out these values. And lastly, after substituting the Rydberg constant for infinitely heavy nucleus and the fine structure constant, you obtained the energy to be R infinity alpha square IC divided by 2 Z to the power 4 of n cube L into L plus half L plus 1 and those terms. And a term shift due to spin orbit interaction is given by this formula, and after this you are getting this. So for the hydrogen like atom, for the spin is equal to half, for J equal to L plus minus half. So this is the derivation. For J equal to L plus half, you get the term shift as this, minus of R infinity alpha square Z to the power 4 L by this term. For J equal to L minus half, you are getting another terms. So here one you are getting minus and you are getting plus. So it shows that there is the one single line has been splitted into two. One is in the upper portion and negative means is in the downward portion. So and the difference between them, we have taken the difference between them, and its value is found out after substituting our Rydberg constant for the infinitely heavy nucleus and the fine structure constant. We are obtaining this value. So and from this equation you can observe that Z value is the atomic number. If the atomic number keeps on increase for the heavy nucleus, the atoms, here you will find that delta Z, delta T value will be increased. So it means for the higher this one atomic numbers elements, you will find the splitting of the line will be larger. But if you consider n means the principal quantum number. If it is far away from the nucleus, then accordingly its separation will be less. And then if the electrons are in the not L equal to 0 means it is spin only, the S only, then S, P, D, F like that. If you consider in that way, then at the time this distance will be smaller. So that is why it also can easily find it out with the increase of the atomic number, and then will be larger, and then it is smaller for the higher n and the higher L. And then I already told you before also the relativistic effect also we have to taken care of. So that is why the Hamiltonian has been given as Hamiltonian, you know, it is the kinetic energy plus potential energy. So kinetic energy formula we have written here in the relativistic correction, and this is the potential energy. So after deriving and expanding the term, you will find that Hamiltonian is kinetic energy plus potential energy, and some terms one my p square 8 m0 square c square is there. This is known as the perturbation term, and the p value you can easily find it out from the this momentum operator. And from this momentum operator value, if you want to find it out this energy due to the relativity, this is the formula, and after calculation you observe this is the energy due to the relativistic term.
This is the Darwin term. Is there a name for this term?
This is the delta T. Delta TR is the this one the shift term, that is divided energy divided by IC. Darwin term ay edu sidana kano gida mo ila ko relativistic term gi do mo na lang. Oo.
Okay.
And the net shift due to the spin orbit interaction is given by this one, the term shift equal to delta TLS plus delta TLR, and this is the expression. So depending upon the value of J equal to L plus half and L minus half, we are finding out this value, and then after substituting the value we are obtaining two equations, and these two equations can be replaced by a single equation, that is J plus half. When J equal to L plus half, you will get this equation. When J equal to L minus half, you will get this equation. So that is why this equation is known as the Dirac equation. And here actually I want to differentiate between the Dirac and then Sommerfeld relation for the splitting of the spectral lines. So here this is the Dirac equation, where all the terms they are all same. The only difference is here J plus half, and here only K. K is the azimuthal quantum number, and this is the only difference, and the others looks almost similar. And here if we draw the this is a diagram of this Sommerfeld level and the Dirac level. Then n, see this is the Bohr level, n is 1, 2 and 3, and for the Sommerfeld level k is 1, 2, 2 means 2 and 1, 3 means 3, 2, 1, and for the accordingly this delta t value has been observed, and for single one you are getting 1.46, and here you will find 0.09 like that. But for the L, here is 1 means 0, 2 means 1 0, and then 3 means 2 1 0. This is the orbital quantum number. Then accordingly J value I have found it out, and the delta D value you will observe that here it is repeating twice. That is 0.056, 0.056. Here also you are repeating these numbers. So this shows that this is called the double degeneracy. So they are lying the same energy. So if you draw the graph here for n equal to 3, k is 3, 2, 1. So this is n equal to 3, k is 3, 2, 1. And here the first one is 0.018 that I have given here. Then next the difference between these two, 0.018 and 0.054 is 0.036. And here for this one spectral term, if you write, then this is the principal quantum number, this is the multiplicity, this is their state, and this is the J value. So accordingly you will observe this value, and here you will find that 3 by 2 and this 3 by 2. One is in the P state, D state, other is in the P state. They are lying on the same line, because this is called double degeneracy, because here this value are the same. Similarly for others also you will observe here. Just see 0.056, 0.056, here you will observe here also is the same thing.
So this is because of the JJ coupling.
JJ. And then here one more thing I would like to mention is in the Sommerfeld model, spin angular momentum doesn't taken into account. And in the Dirac, the spin angular momentum has been taken into account. So because of that, this discrepancy is coming up. These I have mentioned, and here I would like to mention also the selection rule for the transition here. Whatever that I have shown here, the transition that can be taking place from this level to another level, that one selection rule I have given here. However, when we want to observe the experimental and theoretical data, then whatever some of the lines they said they are on the same line, it is not so. Okay, some separation is always we find it out. That is called the lamp shape. So let me just show here first. Here whatever this one they are of the same line, but here there is although the separation is very less, you will observe 0.0105 centimeter inverse, and even here also they are of the same line, but some separation is coming up. So this is called the lamp shape. Okay, so they, even though they are almost the same, but there is some discrepancy is always there, even experimental and theoretical. That is what I would like to mention.
And the lamp shape is due to the correction from the self-energy.
Self-energy, yes.
But experimentally, whether that splitting is observed or single line observed. This one.
No.
Theoretical prediction is something.
Theoretical single line.
So it comes to the point. Dirac equation cannot explain the lamp shape. The Dirac equation, though it is so successful, it cannot explain the lamp shape. The lamp shape can be explained only by quantum field theory. Okay.
Yes, sir, thank you. Then next comes to the electron spin resonance. Actually, I just want to mention this one because here we are. This is also a spectroscopic technique. Here, I mean, some of the, those elements or those compounds which are having the unpaired electrons, they can be easily obtained, can be characterized by the electron spin resonance. And this is also known as the paramagnetic resonance spectra. And here, I would like just mention how it works and all. But even though I haven't used this one, but I find this one to be very interesting because it is all related with the spin. So here, those elements which have the odd number of electrons. Odd number means there will be unpaired electrons only, isn't it? So there is, for this type of electrons, you can easily observe from the electron spin resonance spectrometer. So that is why those transition metals, elements, and all those, if you, those material science groups, if they want to study, they can use the electron spin resonance. And here one more thing is NMR. NMR also one of the things which is related with the spin. So NMR, they use the radio waves, but here in the electron spin resonance, it is used the microwaves. And it lies in the electromagnetic range of 10⁻⁻² meter. And here, it also, as I already mentioned, it consider only the spin magnetic moment, and when it is positive one means it will be aligned along the direction of the magnetic field, because the magnetic field has to apply also. And then if it is minus half means it will be opposite to the direction of the magnetic field. Okay, so let me just show here first. So these two alignment, here this is for half spin, the other is the for spin up, and this is for the spin down. The difference of this one will give you the energy difference G, nu B and B. So G is the gyromagnetic ratio, that value we have already given. Mu B is the Bohr magneton and B is the magnetic field that is applied. And here you can see whatever derivation that we have shown here. When the magnetic field is applied, you will find that the energy gap G, mu B and B. Okay. So here this one actually I just want to explain how it works. This is the Kelstone where the this one microwave will be emitted from here, and when the system is in this one equilibrium or in the stable state, there is on the third line is the dummy load. This is the crystal detector, and this is the sample which is kept between the two poles, magnetic poles. So when it is in the stable state, the microwave will be along this dummy rod and this cavity only. But when the sample started absorbing the radiation, it is not stable anymore. At that time, the radiation will go to the crystal detector. It will be amplified and it will be detected, and then it will be recorded. And then whatever the recorded spectra is quite broad, so that is why we they used to measure in the fast derivative mode like that. And this is one spectrum of the electron spin resonance. Here for different materials, it gives the different spectra. So that is why it is very important which type of spectra is there. That is why there are so many this spectral this one database is also there, in order to differentiate whether this particular compound is in the ESR spectrum or not, which compound is there. It can easily characterize. Okay. And here one more important application for this is it's a hyperfine splitting is observed in here also, because of the interaction of electrons with the nuclear with the nucleus. And you can see here, this is the only single line, but due to the presence of the electron, it has been splitted into plus half and minus half. Then after that, due to the presence of the interaction between electron and this nucleus, it has been again splitted into 4 lines. So this is very important phenomena for the hyperfine splitting of electron spin resonance. And this is one example that I just want to mention. This is methyl radical. So here the this electron, which is the this non pair, only one single one is the carbon, because after interaction with this. And then here, I mean how these 4 lines has been coming up, I can explain, but here is a long calculation is there. But I can explain later if people want to know how you are getting 1:3:1 this intensity. Okay, because here one thing you should know is for the proton H3 is half. For I mean the spin for the proton is half, but here there are 3 protons. So that is why you will get the 3/2, half plus half plus half. So that is why Mi value will be minus 3/2 minus half. This one 4 lines will be there. So accordingly there will be 4 lines, and again transition also will be taking place. Selection rule we have given, delta Mi will be 0. So transition will be minus 3/2 to another 3/2, because it should be 0. That is why minus 3/2 to minus 3/2 minus plus 3/2 to plus 3/2 minus half to minus half, like that. So that is why 4 lines you will observe. Then intensity ratio that that one I haven't shown here, but we can easily calculate by using the this formula. Mi equal to plus half, it is spin up, and the minus half is spin down. So like that. Accordingly, there will be 1:3:3 lines will be there. So that is why what I would like to mention is for different compounds, they will provide the different spectra. So it is very much easier to differentiate one compound to another. This is the one, and then thank you for your kind attention.
Any question, any comment, any addition?
So just one comment. So the LEMSIP is very important.
Mm.
In the sense
Where's the
that-
pen? Where's the pen? Let me see.
So in the sense that, I think, correct me if I'm wrong, Karimai. So this was first calculated by Bethe, right?
Yes.
So Hans Bethe. So this was the cancellation of the infinities, and that's where the quantum electrodynamics was validated.
Oh,
So
okay.
it's very important.
Well, he calculated
Right, Bethe in the
but
trend.
later on, Hyman and all these people will calculate from full quantum field theory. The result is almost the same.
Yes.
So this is the strange part about Bethe, Hans Bethe. Okay. Anyway, Hans Bethe was my supervisor's supervisor. Anyway, I want to add something because I am also teaching in the class. Dirac says that his equation is more intelligent than him. Dirac says that his equation is more intelligent than him because his idea was to make rho positive. Rho means charge density, rho positive. Because in Klein-Coden equation, rho was negative, so he wanted to make rho positive. This is why he wanted to have one equation rather than Klein-Coden equation. That was his aim only. He didn't know about this spin will come. So he knew that in order to make rho positive, d by dt should be there, not d square by dt. In the case of Schrodinger equation. So he want to linearize. He want to write the Klein-Coden equation in the first order differential equation, d by dt and d by dx. He want to convert the Klein-Coden second order equation to first order equation because first order is more powerful than second order. He learned this thing from electromagnetism. In Maxwell equation is first order in space and time. For Maxwell, when you do some manipulation, you will get the second order wave equation. Here the vector properties of B and E will be lost. All information will be lost. You cannot get back the first order again. From second order, you cannot get back the first order. And from the first order, you can get the second order. So in this way, he want to have a first order differential equation of dt and d by dx. From there, you can get Klein-Coden equation, not the vice versa, not the reverse. That is what he is looking. There was a Solvay conference, and Dirac was a young gentleman, like 20 years. Bohr was a towering figure. Bohr asked, during the tea time, Bohr asked, Mr. Dirac, in which field you are working? Bohr asked. Dirac told that, I am trying to write a relativistic equation. That Bohr told him, no, Klein and Gordon had already done, no need to do again. So then Dirac tried to explain Bohr that no, I don't believe their work and there is some problem. But finally the bell rang and Dirac could not explain to Bohr. It was very good because if he could explain, Bohr could publish on the next day. Dirac would miss the Nobel Prize. Okay, that was the thing. And finally, Dirac wrote the first order in space and time, and finally his equation is so intelligent that everything's come out. Spin also come out automatically, not put by hand. Then angular, then your mu, gyromagnetic ratio G equal to 2 come out, mu, magnetic moment come out, everything come out, and you're splitting. And the second, this is one point. Second point, even if Dirac equation is so relativistic, 4-dimensional, once you put the interaction, the relativity is lost. Because in hydrogen atom, your what is called, your Coulomb potential is not 4-dimensional.
Yes.
It is always 3-dimensional. So this is why, even though Dirac equation is relativistic fully, once you add hydrogen atom, that is Coulomb, the relativity will be compromised again to some extent because it is not Lorentz invariant. So things will come like that. Okay, thank you.
Thank you, sir.
Oh, wait. Oh, wali. It is the goal, huh, for you. Okay, it is the goal for you. Okay.
Okay, thank you.
So, our next